Recording this computer. All right. All right, ladies and gentlemen, welcome everybody to CS61C Week 13, once a week live sessions, thread level parallelism week. Woo! Great to see you here as always. Wonderful, 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 wonderful. Let me go to show you the schedule. Here's the agenda for today. So again, welcome to week 13. We have a delightful guest, a Berkeley alumnus. Valerie Taylor is here waiting in the green room, waiting to jump in. So we'll welcome her in a second. And then we have computing the news, as we always do. There's a really big announcement from Apple. We'll talk a little bit about that. We're talking about performance and multi-core machines. And boy, that's what a great launch that we had. And we actually had Valerie, had Apple folks on Monday. So it was like the Monday before. So it was like, they came on Monday and they couldn't say, I think there's something exciting happening tomorrow, but we can't tell you. And then it was pretty exciting. So
it's funny. We had Anand Shilpi in the session, and he couldn't say anything. But his story, went live 6 hours later. So
yeah, it was a good week. It was a good week for our computer architecture. If you're a fan of that stuff. We have an update on the academic dishonesty policy, so some sobering stuff to share. We have a schedule we'll talk about, and then again, we'll have ask us anything. We don't have anything formal to announce about the final, but we had a nice meeting with our students to try to pinch down the time to not have it be a 12-hour final. So we'll talk a little bit about that, but we don't have the official thing yet, but probably next week we'll have the official word. All right. Well, it gives me great pleasure. I'm now gonna invite out of the green room at Spotlight to welcome everybody, to introduce everyone to Valerie Taylor, Dr. Valerie Taylor, a Berkeley alumnus, PhD. She graduated, we just confirmed that Valerie and I overlapped a year when we were both here together. Valerie went to Texas A&M and was the chair, dean also, or just a chair? I know you had some lofty stuff there, much more above.
Right, so I went there as the chair, and then after I stepped down, I became the senior associate dean.
Yeah, boy. So she was dean for so many years. And I mentioned on the slide right here, look at this bullet. She's an incredibly passionate advocate for diversity in high performance computing, which is what the field that she focuses on, and general computing in general. And Valerie and I have been a part of it. Valerie invited me to join her program. Did you found Command It, by the way? Did you?
Right, it was 5 of us.
Okay, so 5 wonderful visionary people founded this wonderful center for minorities with disabilities in information technology called Command It. And Valerie was one of the 5 kind of multi-headed leads of this, which did so many different initiatives. And one of the ones that I got involved with was the Academic Career Workshop, which brings folks who are plus or minus 2 years from graduating, and it brings them together, and we share mentorship. We just basically say, here's what the professorial life is like, here's what the teaching track world is like, here's what industry looks like, here's what working for government labs look like. Just a lot of basic advice to help folks just be very successful as they take their leap into a career with their PhD. So they're all PhD folks, and just deciding where they go. And we've had folks who are part of the military even come in and talk about that. So lots of different ways. Maybe you can work for Pentagon or Air Force, and maybe you work for a national lab, and Valerie will talk some of that. So really exciting to have you here, Valerie. We always start with an easy question, which is, did you always start knowing you were going to be where you are now? Like some people do, some kids go to their book and they draw, on my wedding day, when they're 3, on my wedding day, I'm going to walk down with these flowers. They know the whole thing. Have you always known where you are now? Did you always have that path? Or like, how did you get to where you are? Share some of your history.
Hey, I'll share my history. I'm happy to do that. So it started with my father. So my father is an electrical engineer, actually a mathematician. And so in the house, we always had soldering irons, boards, building circuits. And he and his friends started a telecommunications company. And so, really exciting. So I grew up with electronics. And then when I was in high school, I took a programming course. And I know students are going to laugh at this. So, and I'm showing my age. I programmed with punch cards.
1 and 2. Me too.
Right, once. You had the repeat button, but, and I went to a Catholic school. So the nuns disabled the repeat button, so we could not copy another person's program.
Oh my goodness. So you couldn't do copy and paste. You mean like no copy and paste? Is that what you meant?
No, no. So, you know, and a lot of times, you know, you're working
my
with
gosh.
Fortran, with punch cards, you may have been off in terms of
Right?
putting the
One
character-
column. One column.
So you wanted to scoot over and then, you know, hit repeat, but you had to type over again.
Really, they had to type again. There's something there's value in needing to start from scratch every single time. Oh my gosh, I'm so sorry.
Right.
Oh, and I can't believe you weren't turned off. I can't believe that didn't, like, that experience. Like, people think, oh, well, should I be computing or not? Like, the hill you had to climb for an interest in computing to be, you know, to be able to just do it, not forget to be successful, just to do it was incredible. Incredible.
Well, you know, at that time, it was funny. We had, for my high school, the computer was with the hospital next door. And we could run our programs on a Tuesday and get the results back Wednesday. So we could only run our programs once a week. But that's
Wait, once a week, literally once a no. I mean, I've heard we had to wait a whole day. You're telling me you literally had the whole week was set up for the one big batch run on Tuesday nights to get the result on. Unbelievable.
So
You better get it right the first time. I mean, unbelievable.
You bring your decks on Tuesday and you just run them. Was it IBM 360?
And you know, and it was funny because you did flow charts and flow diagrams before you even wrote a line of code.
Right. You designed it like crazy. You over-designed it, actually, just so you
made certain. You went through on a piece of paper, you know, how things would work, so that way you tried to get it right when you had the punch card.
Wow. But by the way, students know that, by the way, back in the day, people were typing in their PhD theses, 100-page theses on typewriters. Do you guys know this at all? Just want you to know that, okay?
They probably don't know what a typewriter is. I mean, you have to be honest here.
Imagine a keyboard without a computer where you manually the key. No,
it had this ribbon, you know.
Oh my gosh, with the whiteout. Oh my gosh.
No, here's the funny part I have to share.
Go ahead.
That was when I first went to Purdue. I was so glad, you know, they had terminals instead of punch cards. But I had a friend, he said, no, I need to be able to touch my program. So I'm going to stay with the punch card.
Really? Somebody voluntarily wanted to stay with the old, it's like unbelievable.
Oh. But yeah, so things have changed. But I really enjoyed being able to write a set of instructions to actually do different tasks. And it was just like, oh, wow. And, you know, really wonderful.
Here's a question. Did you always know you wanted to go into high performance computing? Like, if you like computing, you were following the path, you know, the rivers were taking you and you were just taking course after course after course. But when did you make that, you know, that's a big navigation point where you say, I want to go into systems, and not just that, but performance and, you know, that kind of thing.
Right.
When did you make that call?
It was when I was in undergrad at Purdue. I took a course with H.J. Siegel on parallel processing. And I was like, whoa, so we can have multiple devices working simultaneously. Now that's wonderful.
What was your language? What was your language that you were using? What were some of the abstractions you were using back then?
So we
go ahead.
Parallel Fortran, I guess.
Is it Fortran, right? I'm guessing.
Parallel
Fortran, it was
right?
That's why I'm laughing. It was still Fortran.
No, okay.
And,
but a parallel version of it.
Right. Well, you had at that time you were using, what was it, Watt 4? I don't know if you remember that.
Not me, boy.
No.
Not me. Not me. This is before my day.
You had a Watt 4 compiler, but then you also had like Fortran 90 that came out that was doing more in terms of parallelism. So yeah, and I programmed, what is that? In grad school, that's where I was programming on Intel Paragon.
Okay.
You know, yeah. And so Intel has been in the HPC market for quite some time. They were in the HPC market with the Intel Paragon, then they went out of the HPC and you know, came back. But I even, what was it? And it wasn't parallel, but it was just a big machine. Did some programming on the PDP 11780.
Sure.
Yeah. So, because that was at my father's company.
Oh, okay.
Oh, digital.
So you went from a Purdue undergrad where you kind of touched a little bit of the parallel stuff and you liked it. when you applied to Berkeley, did you say that's what I want to do, or did you apply for kind of a general CS thing, systems, and then decide HPC of the systems angle? Like when did you and who did you work with when you were at Berkeley also?
Okay, so at Purdue, after undergrad, I stayed there for a master's.
Oh, okay.
And the person I worked with was Jose Fortes, and doing a lot of work in systolic arrays, which are SIMD. So systolic arrays are just SIMD machines, and they call them systolic arrays because it models the systolic system of pumping of the heart. You're pumping data because you're just having a single instruction and you're pumping data through the machine. Oh, so every cycle you're doing these instructions, but on different data. And so, yeah, so they had these machines. It was a systolic array. They came out it was NCR, which was the National Cash Register company, came out with systolic arrays. So we were doing some programming on those and actually looking at how to map applications to those systolic arrays. The interesting aspect was that the processing elements were 1-bit units. So we had to break down everything in terms of 1-bit computation. So you would break down your I know.
Wow. Okay. So you're doing it with a float. You're telling me you're adding 2 floating point numbers by doing something on the bits of them, not just by saying float 1 plus float 2 equals float 3. You're saying you're literally going into the bit and understanding what each one. Well, you got to know what the bits do. I mean, my goodness.
And it was very interesting because the reason why you work with the bits too is because of the data dependencies with the bit level. And so, yes. So but it was fun. So then when I went to Berkeley, at that time, they were doing work with, it was Sprite operating system.
Sure, Osterhout, those folks, right?
Right. And also doing work with RISC.
Yeah, right. That was the early days of RISC. That's the early days of RISC. And RAID was also in those days. I mean, Randy was working on RAID. Dave and team were working on RISC at the same time. Yeah.
Yeah. And John Osterhout was working on Sprite.
Wow.
And so, what I did, I worked with a professor in EE because I also enjoyed signal processing.
Oh, okay. So Bora is a EE faculty member. So we're crossing Hearst Avenue in teaching this class, which I think of this class as really the single class that forms the bridge between the two fields. Who did you work on the EE side?
So it was David Messerschmidt.
Oh, sure.
Right. And David he's well known for adaptive filters and signal processing. So
you were actually, that was your application of your parallelism, or that was the application of the program your research was on that project.
Actually, so here's I never go down that straight path. So when I started working with Dave Messerschmidt, he said, hey, why don't we look at applications outside of electrical engineering, computer science? So I started looking at applications with finite element analysis. So I took a structures class and started doing work in really computational science.
Right, I was going to say that. It feels like the heart of computational science. The moment you say, let's take what we can do, but apply it to a scientific problem, that seems like computational science writ large. That's perfect.
And the funny thing about, systolic arrays, they were popular back then for people were trying to map all kinds of applications on systolic arrays.
Right.
Had limited success until now. I mean, all these neural processing engines are essentially systolic arrays. And last month, I reviewed a paper for Journal of Solid State Circuits that implemented 1-bit systolic arrays. So they went the full circle.
Look at that.
Right. And,
it's old is new again.
Right. And my research was in, with finite element, you end up with sparse matrices. So, so it was looking at architectures for sparse matrix computation.
Right.
Yeah. And you're
incredibly popular these days.
So now here's the fun part. When you got to Texas A&M, you get to chart your own research path. What was like the thing that you said, I want to get grad students and get a group behind me to work on one problem? What was the thing that you were like most hungry to work on when you left Berkeley?
Well, okay, when I left Berkeley, I actually went to Northwestern.
Oh, okay. Sorry.
So,
Yep. All right.
yep. So I spent about 11 years at Northwestern, and it was so interesting because at that time, I finished computational science. And so I went to my first supercomputing in 91, and I was presenting a paper, and everybody said, given you're at Northwestern, you have to talk to, and they were like, Rick Stevens, he's head of the mathematics and computer science at Argonne, and they said he's a tall guy with long hair. You go supercomputing, and you kind of go, that kind of describes a lot of people.
in 91, right? That was the look.
Just gotta go. I was just like, can you give me a little bit more?
That's
but
funny.
I finally met Rick, because I didn't know Argonne, even though I grew up in Chicago.
Sure.
So he was just like, why don't you come out, give a talk? So I went out, gave a talk, and it was just wonderful because there were so many people doing work in computational science that I just felt like I found my community. It just was wonderful. They had computing resources. So at that time, they were getting a J machine. So I had a chance to program on the J machine, with active messages and
that's great. And when you got to that community, I'm sure the community was remarkably diverse and remarkably full of women and full of people of color and disabilities, right? I'm sure, right? Wrong.
No.
Right. So is that what got you thinking? How do I bring other folks into this family, into this umbrella, into the tent? How do we have a big tent approach?
Right. You start to say, well, I don't want to be by myself.
Right. Yes. Across those many dimensions. Right.
That's it. And so I met, who is it? That's how I met Bryant York. I met Roscoe, Roscoe with HPC. And so it's wonderful. It's been a great community because initially I started going to the ISCA, the computer architecture conferences, but I was doing application specific. And at that time, it was really general purpose because you were right in the heart of Moore's Law. So, it's not where anyone was looking at the advantages of application specific. But then when I went over to the HPC community, where, everything is looking at sparse matrix, sparse matrix computations. One person I talked to, I said, well, given you work with all these science, domains and different applications, I said, do you have any examples of dense matrices that result, because the sparsity is because it's not the case that if you have a large system, something, one particle or one object will interface with something very far away. Usually the forces are not that strong. So usually you're working within a neighborhood, which gives you the sparse matrix. And he just told me, stop looking, there are none, move on.
Interesting. So the problems are always localized. I mean, if you think about most of the things that are happening, like, a climate simulation, if there's a hurricane here, it's not going to affect a hurricane on the far side. Maybe eventually it will, but things are all local. I mean, and that results in a sparse matrix as a result of that. That makes sense. Yeah. Stop looking. That's fascinating. And so then you get to at some point you moved to Texas A&M. Is that right? That's when you and I more overlap with that. And at that point you said, let me have a both. I don't know how you managed, by the way. You were like one of the busiest people I've ever met. How you both manage the leadership of this wonderful group to bring outreach to all these folks, as well as maintain be a dean, and as well as maintain a research agenda. Like, how do you have all those fires burning at the same time? Like, how many grad students would you have? And then would they find the problems, or would you find the problems and hand it to them? How did you have that conversation in terms of your own group?
So with my own group, a lot of times, you have senior grad students and then you bring in a new grad student, and then they're all working together so they can see what the senior grad student is working on. And usually, and I always say this, when you're working on a master's is really good, and you answer some questions, but usually a master's will give you more questions than you answer. Then when you go for a PhD, I always say a PhD, you still have open questions because you've made some assumptions, but usually you answer more questions than what you'll have at the end,
Then you create, yeah.
Right. But a master's is just very fruitful because you'll start down the path, you make a lot of assumptions, and then you realize, and you'll say, wow, okay, this works for this narrow case. What happens if I go here or go here? But then you go, I'm at my 2 years, so I'm ready to go. Bye-bye.
Interesting. So when you have students who leave with the master's, I'm sure you have, I certainly have as well. Do you feel like there's a missed opportunity? Feel like, oh, if you'd only stayed, there would have been such good so close. We were so close.
You do, but then you say, but it is based upon what you want to do.
Right,
So,
right, yeah, sure.
yeah.
And there are actually, a wonderful career paths for people with just a master's. I'm just thinking if this is part of a mini advising session from our audience, as you're thinking about what you want to do, there's certainly a ton of opportunities in industry right now. It's very, very hot. You could also think about a PhD. As in advising, I tell them there's a grad school for everybody. It's not only about the Berkeleys and the Stanfords and the MITs, and there's a lot of great places out there that would love to have you. Certainly love to have a Berkeley student. So it's just thinking about if you decided to get a master's, and funny thing is you can go to a master's and sometimes you go for a PhD and you can get a master's on the way to the PhD as kind of like an anchor point. It's almost like you're rock climbing and you want to tap in a piece of anchor. I just came back from Yosemite, so I'm kind of thinking about these analogies here. You tap in a piece under the rock in case you fall, in case you decide it doesn't working out, life changes, you get married, you have a kid, and then you have at least the master's to hang it on. Otherwise you fall back with all that work and you got nothing to show for it. So the PhD, always we encourage our master's. But sometimes you get into master's and you get excited. It's like, wait, I want more. So you only applied for the master's and you see like, wow, look, all these things I could do. You didn't even realize how much fun it is to do research as a grad student. And then you decide to jump more.
Yeah, and that's just what happened. After I got the master's, yeah, you want more.
So did you come in for the PhD? Did you come in for the master's and decide to get hungry when you got here and want the PhD after that in terms of your own career?
PhD when I went to Berkeley. I finished the master's at
right. Sorry, right, that's right. That's what I meant. Yeah, you mentioned that. You mentioned that.
And see, after I finished the master's, at first I only wanted the master's, but then I ended up working on research instead of the coursework only, because I was like, courses, that's wonderful, but I'm ready for something a little different. And I just love the fact that you're given an open problem and there's no one solution. So I always go, when there's no one solution, I can bring, my full self to the problem and answer it in a way that's comfortable for me. So that's the part I so enjoy versus feeling like, there's only one, you have to get this one path right. So I enjoy the research that gives you that open space to just explore.
Wonderful.
We have a question from one of our students.
Sure. We have Q&A. Yeah, perfect. Yeah, somehow.
Ben is asking, what technologies do you think will be the key to creating the next generation of supercomputers to advance the field of HPC?
Oh, what technologies? That's a good question. So I think a couple of things. Because right now you're seeing supercomputers where you have CPUs, a multi-cores, and combined with GPUs. But you're also seeing a large number of AI accelerators. And that is, you have the accelerators like Cerebrus. You have the accelerators, Samba Nova, that's with, I think, Kunle at Ola Colton at Stanford. You have GraphCore. And so with applications, and I primarily focus on scientific applications, you're starting to see also with those applications where those applications are incorporating AI methods. And that could be AI methods for surrogate models. And so I think you'll start to see more, heterogeneity in the supercomputers. Then you're also seeing work that's being done in the quantum space. And if you look at, for example, IBM came out with a roadmap with the quantum space to say, 2023 was the projection for about 1,000 qubits. And so that'll be interesting, as well as to, what we will explore in the quantum space and having that connect as well with supercomputers. So I think, in another area, and that is you're seeing some work that's being done with FPGAs to do more in terms of domain specific or application specific to actually, let's say, work with a particular complex function. So I think the technologies will be along multiple dimensions where you'll have different accelerators. Right now we're seeing a lot in the AI space. You'll continue with CPUs, GPUs, possibly FPGAs. And then I think also as we get more in terms of larger scale quantum systems with larger number of qubits, that'll be interesting as well. So I think it'll be supercomputers will move toward more heterogeneous.
It's like a many flowers blooming phase right now, right? Kind of a thing.
Mm-hmm.
Wow, there's more questions. Bor, do you want to share that?
Yeah, I will. I mean, but we may have to change this class in a few years, so that's kind of worrying me.
We just finished the videos. We just finished off the video.
Yeah.
No.
Do you know somebody who knows how to program these kind of things that you're talking about? Because I don't know anybody.
Right.
So here's the part. I think right now you're seeing a lot, with programming CPUs and GPUs. Where with GPUs, you're seeing a lot with the CUDA programming. I think Intel is now talking about one API.
Right. I was going to ask about one API, whether there is a way to kind of have a software layer above, like an abstraction above everything, right?
Right. Yes. And then you're seeing the work that's being done with the quantum computers in terms of where the quantum work is not where it's connected with supercomputers at this time. I mean, you have a small number of qubits in the range of 100 qubits. So you really want to get to about 1,000 qubits, until you get to something interesting. So you're seeing that work that's done with quantum is not done in terms of a connection with supercomputing. And that's where you've seen a number of centers that were just announced in the quantum space. And I think, it will be a question, and it's a good, question to ask is how to program those systems that's very, heterogeneous. And the question that would come up is, what becomes the compiler that will do the mapping of applications to these particular components? And I think that's a really good question that you're seeing research that's being done in that space.
Right. Yeah, well, we mentioned actually, that's on my slide. It's like, it says this is a hard problem and this is an open problem still to be, you live in some language, you live in C and automatically parallelize your code, automatically map it to all the different devices in a really efficient way. So that's still, again, an open problem.
Right. I'll rephrase the next question a bit. I would rephrase it this way. Which kind of previously intractable problems can be solved with better hardware and parallelism? And they're asking about some of these NP-complete problems that are out there. So which one? What's the big problem that we need to solve?
That's a really good question. That's a very good question. And I hadn't thought of that question in terms of NP-complete problems and looking at it in terms of heuristics. I will comment because today I was attending the supercomputing conference. Okay. And
SC20, yeah.
Right, that's now virtual. And the one person, Bjorn Stevens from the Max Planck Institute was talking about climate modeling. And he was talking about the parameters that are needed in terms of doing the climate modeling. And he talked about this one parameter for which he was saying for such a long time, it's not where they had the compute power to be able to, solve for this parameter. But he noted, he said, exascale computing is, you're looking at that in next year, 2021. So DOE has exascale computers at Argonne as well as Oak Ridge for next year. And so that 10,
you feel like this, you're like, I cannot wait to get a hand of that, right? I'm sure.
That's it. Yeah, so you're looking at a billion operations per second. So then he started talking about, he said, you know, when we start to look at the scale of the problem that we want, an exascale computer, we're now at the point of having this exascale computer in which we can actually look at solving those problems. And so, you know, he was saying now we're at the point of having some detailed models that we can start to use with climate modeling. So I bring that up. It's not when, you know, addressing the question about NP complete problems, but just complex problems in general that need that level of computing to actually solve some of those problems. And then you'll go the next step. Now that you have the models and the detail of the models to look at all the different interactions, you can start to do what if scenarios. And that is to say, what if this occurred here? How does that impact climate?
Right. What if we had at least somebody at the front office who's having some climate legislation? Oh, okay. How could that? Let's just say somebody who believed in climate change and was having some legislation. How would that change a number? That kind of thing. That's a good thing. Yeah. I mean, what I've heard from folks, there's a similar thing I've heard Valerie say that I've heard other places, which is all faster computers let you do is work on larger problems. Like you were saying, you had little toy things you could do and solve completely and work on that. But as the computers get faster and faster, and you're at the exascale, by the way, XB 2 to the 60 something, remember XB 2 to the 60 is number of floating points operations per second. Now all of a sudden your input size can be bigger and you can now do it in reasonable time. Rather than waiting 50 years, you're now waiting a month, you're waiting a week, for that kind of thing. So you can work on higher resolution, larger problems, same kind of thing, but nothing fundamentally different. The only thing that's fundamentally different, what I've heard is quantum. Quantum is fundamentally different in terms of what it's going to give you, but everything else that's not quantum is just bigger things, a little bit fast, a little bit faster, 10 times faster. It's not really cracking a nut that you couldn't crack before, just a larger problem size. I think that's it.
It is, but I would say that larger problem size is important because, for example, you can take something and the granularity that you may be able to do is something that's 10 kilometers, and you really need something that's 10, 10 meters instead of 10, kilometers. But you can't do that because it would take, months to get the results. Now you can start to do that type of model. So it is the case, you're doing something bigger and faster, but it's also, you're doing the analysis that you haven't been able to do.
Right. Yeah, Kathy Yellick, you know Kathy Yellick well, I'm sure. Kathy always shows this video. No, in the CS10, in our non-majors BJC, Beauty Enjoy Computing class, she always shows a video of, here's what happens if you model hurricanes at 10 kilometer radius. And you see these blues and this, and here's 1 kilometer, and you can actually see the eddies. Like there are things that you get revealed. So it is fundamental. When you go to higher resolution, you can see things you couldn't see before. And because of that, the scientists are like, oh, wow, look at that. And they make some new theories based on that. So it is the case that higher resolution can be transformation in terms of the analysis you can get of the data itself. Wonderful.
Right. Yes.
Boy, you want to take the other ones? You want to?
Yeah, here is another question.
This is fun.
More
this is
kind
great.
of a personal question. We have a limited amount of time, so maybe a couple of more.
Yeah.
I feel that an additional 4 or 5 years in academia for PhD will be challenging to enjoying the other parts of life, especially after 18 years in K through 12, 2 years community college, and now 2 years in Berkeley. At the same time, I'm fascinated in exploring more in ECS. How do you balance your options to pursuing another 4 years in academia in grad school versus going into industry immediately and be free of academia?
Well, here's how I balance. I look at the fact that you'll be working 40, 45 years of your life once you get out of school. So 4 more years, that's, that's like that 10%. So with 10%, spending 10% longer in academia can open doors to where I'm that 40 plus years that I'm working, I'm doing what I enjoy. And that's the part that made the difference. So I'll give you an example. When I was at Purdue and I finished a master's, I interviewed after the master's because I thought I wanted to finish, and just work. But I wanted to go to places that were pursuing research because I so enjoyed the open problem of, not having this one path. And every place I went, people told me the same thing. They said, you don't want to come here without a PhD. I was like, really? They were like, I said, and I thought, but they're interviewing me. They go,
They don't mean it.
You paid for the flight. I'm here. But you don't really want me or what? What is it?
I said, but if you want to actually have more input and actually steer the direction of where you're going, you want to go for the PhD if you want to do the research. And so, and that's when I decided to go to grad school, is that to continue on to grad school and get the PhD. And in grad school, I had so much fun.
Me too.
I got a chance to interact. So it wasn't where I felt, and grad school is very different from undergrad. In undergrad, you have a few electives, but you're primarily taking the courses, the required courses. In grad school, you're taking the courses that are of interest to you, which makes a difference. And then you're exploring problems that are of interest to you as well. And then you have a lot of friends that are in grad school, and we were doing fun things in grad school. At Berkeley, when I started there, we would go, sometimes on a Saturday, hang out at the beach. We had, I went to tie-dye parties, because of course that's what you do when you're in Berkeley. And but we had a good time. We went to concerts. So you get, there you have a friendship that forms in grad school, where today I'm still in contact with, many of the people I met in grad school, because you have this bond where you're doing a lot of work, but you recognize you need to take breaks. You need a balance. And it's not where you're just working 24/7. You're enjoying yourself as well, but have a focus on research. So it's a really good time in grad school. Yeah.
One kind of related question, or opposite question, say, what motivated you to leave from your professorship and go work at Argonne Lab? Do you still advise grad students? Is another question. Maybe there are potential candidates over here.
Well, actually, it's very interesting. So when I was at Northwestern, I had a joint appointment with Argonne, and I organized my teaching schedule such that I taught on Tuesdays and Thursdays, and I was at Argonne on Monday, Wednesday, Fridays. So I had an office there. I was interacting a great deal. I thought for me, I had the best of both worlds, of Argonne with the community and also the resources, and also teaching, doing research, grad students. And so then I went to Texas A&M, and I missed Argonne and that interaction. And when I had a sabbatical at Texas A&M, I actually went to Argonne for my sabbatical. And Argonne invited me back to give a research talk, which I was excited to do. And during my research talk, I was talking with different people, and Rick asked the question, are you ready to return? I hadn't thought about that. He was like,
Look at that.
Yeah.
Look at that.
Mm-hmm.
Do you still mentor grad students? Do you still work with grad students as well?
I work with grad students because, for example, I work with professor at IIT, and we work with her grad students, or if I work with someone at U Chicago, but it's not where I have a tenured faculty appointment. And, I could pursue it, but it was just right now, especially being a division director, I focus on Argonne and interact a lot with collaborations there.
Yeah, that's a busy job, being a division director.
Folks, do you realize who we've had on these calls? We have the lead from DARPA, the division director here. I mean, this is amazing. Thank you for taking the time, by the way, from your busy schedule, for all the things you must be doing. My goodness, that's just great.
Yeah,
it's a good time right now.
That's true. Maybe it's because holidays coming up, if it's a little quieter kind of a thing. That's true. Yeah, that helps a little bit.
Right. And you know, and supercomputing is this week.
Oh, that's right. Yeah, the conference. So the whole lab is going to the thing.
You
Right?
know, so you usually have supercomputing, and then you have to have it followed by Thanksgiving so you can get that break.
That makes sense. Yeah, that makes sense.
Right.
Sure.
And I
Sure.
think,
Sure.
Mm-hmm.
Boy, what do you think? Do you want one or two more?
Yeah,
Or,
I think we are out of time.
Maybe take us out, Valerie, with one thought, which is our students are now doing, as I mentioned before, they're doing SIMD parallelism, thread level parallelism, data level parallelism with MapReduce and Spark. Tell us, give advice, tell us what thoughts you have for a group of students kind of going through the stuff that you do, but they're touching a little bit. They're not really going deep into any, but they're touching here, touching there, small projects here. What's the advice for a student who likes this stuff? What's your advice for people using this stuff? What's the, maybe here's an example. Is it maybe use a functional approach, because a functional approach means that you don't have to worry about the order of operations, live in a functional language. What is some advice you have for our students going through the work now?
Okay, here's some general advice. So I'm not going to give you, because the general advice is to be curious and to try different approaches. So for example, a lot of things that we do with different applications, we do a lot with MPI with OpenMP. And the OpenMP gives us the thread level on a given node, and we do some, and you also combine it with some CUDA and MPI between, but be curious and explore and see what happens under different scenarios, because that's the way to really get an understanding of what's going on, is to try different things. And it's software, and if things don't work, it's okay.
It's not chemistry.
That's it. It's okay. And
wonderful.
Right. So take that opportunity to explore things and know it's okay if things don't work. You can try different things, start off with something small that's working, get an understanding, explore different pathways, see what happens if you change some parameters around.
That's great. They actually we're launching them to Project 4, which is an optimization, try to make this code faster. And we're not telling them how to do it. So we're giving them hints in here, but again, that's a great advice to them. Play with different things. Try this one. If that doesn't work, try the other one. Maybe you can loop unroll. Maybe you can do something here. Maybe you may play with more OpenMP and optimize your loop a little bit. Think about what that is. That's a great advice.
Right. And you can do blocking,
Right. Cache blocking.
Right. It's so many. Here's the question too. Do you also, the students get access to different profiling tools as well that may be available and give you, more insights into what's going on, and maybe hardware counters. And
where are you losing your time? Exactly right. Yeah.
Right.
Wonderful.
We haven't covered those in class, but they're very, very useful.
They are.
Wonderful, wonderful. Well, folks, let's give Valerie a hand. Thank you so much for joining us, Valerie. It's great to see you. Thank you for taking the time, Valerie.
Woo,
amazing. So great. I love these. This has been so good to see all these old friends and meet some new ones. It's just thank you again for the time, Valerie. This is great.
A pleasure. Love it. Thank you for the invitation and enjoy.
Yay. Thanks again.
Thank you.
Thanks again for joining us, Valerie. Perfect. All right.
Bye-bye.
Take care. Bye-bye. Perfect. All right, so we are up to the next slide, which is a quickie computing the news. I've got 6 minutes left. We have 5. Let's cover this. You all saw, hopefully you saw that, and that's actually, saw a couple of responses to a long thread about this. Apple's new hardware release of their own silicon. We kind of knew that it was coming because they talked about it at WWDC, but it actually hit, and we're very excited to see some of the results that they're talking about. 8-core GPU, 8-core CPU. We're learning about that this week. I mean, this is the TLP week where we talk a little bit about how that works. 16-core neural engine, all these things on chip. I saw memory on chip. I was amazed by that, brother. If you saw that. Memory's not in Sacramento anymore. If memory's on chip, that's a whole nother conversation of what happens. Right? It's like caches are on chip, but not memory. So it looked like memory was going to be on chip.
Memory is in the package. Memory is in the package. So I think that this is like... that's the biggest advantage over here.
Yeah.
So it's not, memory is not in Sacramento. If you're in Berkeley, it's like they built a freeway now to keep Costco in Richmond. So memory is in,
right. But and
Richmond accessible to freeway. Yeah.
Yeah, it makes sense. I love the analogy, but it also, I mean, that's going to make it, if someone says, Dan, how do you make your computer any faster? I say, buy more memory. Like have the Sacramento trip, something that you don't just have to pay all the time. That's a way to fix that. So they've certainly hit that. And here's the slide. Dun, 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 dun. This is the fastest Apple computers. They looked at the whole lineup of what they have, and the three M1s. I just want to say the three M1s. You can see, you can't see my screen. The three M1s in the top 3 bars are all the new M1 machines. These are, by the way, not even the highest end machines. They normally have a higher end, MacBook Pro. They have the Mac Pro, but we can't wait to see what that comes out when they put the M1 chips in there. But I want to point out the red curve, which is the 4th fastest computer on the Apple lineup. is the M1 chip running in emulation mode of the MacBook Air. Do you realize that? The Core i9 is slower than the M1 chip emulating the Intel. Unbelievable machine. So this one to share.
This will be fun to see on real world applications. I think it's, the running things that look...
That's some benchmark. I don't know what benchmark this is. I don't know what the benchmark is.
Yeah, this is going to spend... this will be very interesting.
I'm excited. Okay, so that's exciting. Let's get heavy for a second. Let's take a step back. Bor, you want to take the lead on this one? You're the one who've been mostly working with this, but we can share and tag team this one too.
So unfortunately, I mean, during the semester we have been doing some code comparisons, submission comparisons in this class, and we are finding a substantial number of cases that look suspicious. Put it this way. Some of them are obvious. There was an obvious plagiarism that happened. So we need to maintain the integrity of this class. Nominally, what we said on our course webpage is that there'll be some severe penalties. And what we said that in this scenario, we are going to in the worst case scenario, we are going to give you an F and send you to the Center of Student Conduct to resolve the situation. We know that this is stressful and these things happen, and we would like to offer a modification to this policy. We are offering students who made a mistake to come forward and confess. We don't want to coerce anybody into confessions. We are offering here, if you did something wrong and you know that you've done something wrong, you're going to have a reduced penalty by admitting that you've done something wrong. That'll save us time and that'll help us a lot. But if you admit it and we find you're one of those people that we have on our list of suspected academic dishonesty, we will just give you 50% negative points on that exam or on a project. We're not going to look at the assignments this semester. There is no point of doing that. But we're looking at projects and the exams. So 50%, so instead of getting 0, we are assigning negative 50% penalty because you could have just submitted nothing and don't put anybody don't given anybody extra work to trace that down. And this will result in a non-reportable warning at CSC that is not something that is visible to anybody. It is just there if the offense gets repeated. There is evidence of that, so it's known that it is not the first time. There's more severe consequences if this gets repeated, but the first offense is nothing. Stays sealed in there.
This is part of the Berkeley's 2-strike policy, basically. So they say everybody gets to make one mistake, and so this would be, if it's just your first mistake, and that information about that academic dishonesty goes into a folder, and no one can look at it. That's an important piece. There's a second slide here. So we're going to have a form available to fill out, and we do not want to coerce anybody. So stop listening if you've been walking a straight line. But if it is, it's giving you a chance. We will not automatically fail you on a project if you come forward with that.
And so I want to add, so I actually went and looked through some of these cases. Some of them are, unfortunately, completely obvious, and we can just assign an F and send this to the Center of Student Conduct. But we're not going to, at this moment, we're allowing anybody to come forward and take a reduced penalty. Things happen. Now, if you don't do that, we will have to look through the code and establish facts. It is not just going to be, some software tool looking at things. It will be humans that are going to determine whether there has been a case of plagiarism. And it takes time. So we have to assess at that point more severe penalties. They are going to, in some cases, if those cases that are obvious, we don't really need to have a hearing. We can just forward this straight to the Office of the Center of Student Conduct and assign an F in the class, and we don't have to spend too much time on that. There are some cases where I'd like to hear your opinion and would invite you to tell us, how, is this possible? What are the chances that this kind of coincidence happens? There are no further pleas at that time. This is just basically determining what is the penalty for plagiarism. There are some, but we don't want to curse anybody. What we would like you to, if you're not sure, if you knew that you blatantly copied something, just tell us. If you collaborated a little bit or a little bit over collaborated on something, and again, this does not apply to exams. In exams, there is no collaboration, but on a project, it is possible that you have talked to friends. If you did
you had a
something
bug and they helped you a little bit with the bug to debug, and next thing you know, they helped you a little bit too much, and now your code doesn't look like theirs, but it wasn't digital, but there might be a little bit where it's too close because of how they were helping you and how they helped you fix your problem, and now it looks kind of like their code and how you fix your problem. These are all squishy. These are all squishy here, these lines.
Yeah, in most of these cases, it may happen that you have crossed the line. But if it is something that it is not clear, feel free to ask us. You don't have to admit anything. Ask us, and we can help you figure out whether this was right or not quite right. Not, in the spirit of academic collaboration. So. This is going to go on Piazza after the class, and there'll be a link over there with the Google form to be filled out. Be specific.
Yeah, and that's the line of communication. That's the cleanest way, because we've got 1,000 students. If we just have email, I don't want to get lost. I just make sure nothing gets lost. So go through that form, and it'll all be there on a sheet. We'll be able to find that. Yeah, go ahead, Bor.
If you did nothing wrong, just forget about this.
Yeah,
you're free. Go. No need to deal with this.
Yep. There's a quickie. This is actually from the Center for Student Conduct, and so what you're seeing here, nobody can see my cursor, but in the top right it says something suspected, and the meet with students, or so this instructor does not meet. On the right, it goes straight to basically the disposition form. It goes on to there. If you meet with students, then you can assume responsibility and do this. Otherwise, your student does not assume responsibility. So the meet with students, this is the part that we're having the form for. This is the kind of thing, this works great for a 10-person class. This does not work great for a 1,000-person class, to have all those meetings. So we're putting this form to kind of basically let you say the things you would have said face-to-face, but you're saying it, in a written form that we can review and have that. So, because oftentimes nobody ever records these face-to-face meetings, and so some information is lost. So essentially this first top left bullet that says, instructor meets with students, this is the chance to have that conversation. So whatever you would have said to us during a meeting, you're writing down on the form, and that's what we're taking, and we're making a decision. And in that form, you're either assuming responsibility, which you follow the left block, or do not assume responsibility, the middle one. And it might be something where you need to talk about it some more. I'm not doing either one. I just want to tell you what happened, but I don't know if that's actually crossing the line. That's the part that's kind of like a third box. So I'm saying I still need to kind of have a conversation about that. So there's a third option where you say, this is what happened. I don't think I cheated. I don't think I cross the line, but I may have. So that's the part that's in the middle that will engage, that a human will come in and have some conversation with you and figure out what that is. Oh, I lost you. I lost the audio. I lost audio.
Please respond to Piazza privately, to a Piazza post if you're like, hey, this is what happened. Should I fill this out? And we'll respond. Yeah. But again, if you do not respond, if you don't admit any of this, we'll give you till Thursday to respond to this. If you don't, then we have to come to you with the evidence. In some cases, we are going to just notify you. In some other cases, we're going to invite you for a conversation.
All right. Anyway, it's tough stuff, but we don't, we really
take
this
seriously. Is not something that is fun,
we take this
but
seriously.
It happens. It happens, yeah. And it
happens every year.
Integrity of this class.
Yep, definitely. All right, let's take a breath. Let's do a quickie thing. We are scheduled really fast. We are in week 13. We have 3 weeks of class left. There's an RRR week and then an exam. So we're looking at 4 weeks from the exam. I believe next week we'll be able to have a conversation about what the final will look like. But we're trying to have a final that looks like the old school. That's our spirit. We're actually going to the design session for the final to make it look like the old school exam. The old school paper exam was a 3-hour session where our TAs could take it in an hour and a half, but you had 3 hours total. That's what we're looking at our design space. So we're hoping to get that kind of thing with Prairie Learn. So we're going to be in Prairie Learn and ask the kind of questions we used to ask in the olden days, in which if there's any code, it's a very small line of code, very small, probably not even asking you to code in RISC-V, probably not asking you to code C. You're filling in a line in a box, not using that. So you're not going to be, we're looking at the current design to not have you code C or code RISC-V on your own. It might be write the C code that does this, or fill in 3 lines of this, but it will not be with the benefit of Venus. That's what we're currently looking at right now. And so we'll figure out where the partial credit can be for all those things, but that's the current space we have for that. So this week is TLP, Thread Level Parallelism Part 2 and Part 3. On Friday, we've got MapReduce and Spark. This is all the parallelism week. It's wonderful. It's like Shark Week at the Disney Channel or the Discovery Channel. This is Parallelism Week on the 61C channel. And then next Monday is the last lecture on parallelism, data centers, and cloud computing. Then we have 2 days of a Thanksgiving recharge and rest. And I wrote here that Project 4 is due on 12/2, which is the Wednesday after Thanksgiving. I said we move that to give you some time after Thanksgiving to come on back and finish up what you need to do. And if you still have leftover slip days, you can use those so that, this in theory could even push 6 days past that. That's what we've got.
Officially 3 days for Thanksgiving, actually. Wednesday
Yep, that's right.
Through Friday.
Correct. 3 days of Thanksgiving, Wednesday, Thursday, Friday. Exactly. All right, almost done. And actually, that was my last slide. And we're already 8 minutes over. Okay, so I'm looking at questions. I enjoyed writing my own code. Well, you might be able to write some code, but just very small amounts. But we're looking at our design space is not to ask you to do that. I'm not officially declaring it yet, but our design space is to not have you to look more like the old school 61C finals, and all those are available on HK, and you can look at it. And we'll try to give partial credits whenever we can. We'll do that there. Let's see. Can we cite and use other papers and use their cache blocking method? I think that'd be a wonderful idea, right? Do research on how to do this better, and as long as you refer to it, that'd be great. I think that's a very reasonable thing to do.
Yeah, that's an absolutely brilliant idea. Just do it.
Brilliant idea. Yeah.
Just don't copy somebody else's code, because
exactly.
then there is a possibility that someone else has found that code, and then our similarities software finds all of you.
Exactly. Midterm scores were delayed partly because if you know this, but many of you who took the midterm retake happened this last weekend, and there was a ton of time. We have basically an inner circle team that's working on exams, and they're the folks working on the auto graders. They put together a very early rough draft for auto graders that was able to inform. We didn't want to have to make everybody retake the midterm. We had a list of, I think, 200 or 300 initially. We kind of pruned it down to, I think it was down to less than 100, Bor, if you remember, the 100-ish, plus or minus a little bit.
90 something, yeah.
Yeah, it was very nice. So we used that first auto grader for that, but they were all spending time on this, and they all spent time on helping answer questions on it. It's our inner circle team, our exam team. So they were helping with the exam, making the midterm retake happen. We're just about ready to release the midterm grades. So I'm sorry for all this delay. Thank you for your patience. Certainly, thank you for your patience on all this. We wanted to do it right. It's much better to wait and do it right than to do it early wrong, and then there's all the flame, blah, 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 and then make the scores go down. We don't want that to happen. We want it to be, here's at least the minimum scores, and your score won't go down. So that's the idea, a goal for the midterm auto graders that we're running this stuff through. So that's really quite important, and to do it right, and that's why it's taken so long. There's one question, which of the assignments had these issues, had some of the cheating issues? And I think, Bora, we've seen cheating in all 1, 2, and 3 so far. Is that right?
Yeah, we have seen them in different places. I mean, people will find out. Yeah,
it looks bad. And people are giving some feedback on the coding session they're doing. They thought the midterm retake was really good. So I'm happy to hear that. That's great. And here we go. So ETA, we're trying to get midterm scores back this week. That's our, fingers crossed. Again, it's better to be right than fast. What's the 3 boards? You can either be cheap. Well, no, you do it right. No, there's 3 things. You can only have 2 of them. What's the 3? God, what is the thing? Do it right. Yep. Do it cheap. Anyway, you can't do it right, cheap, and correct. And so the idea is better to do it slow and correct. I forget. I'll get it. 2 seconds after I cut, I'll remember what it is. But we're gonna try to do this right, and don't want to have to go through many iterations of it. So we're really trying to do this. We don't want to make it fast, right, and cheap. You can only have 2 of those 3s. Exactly. Thank you.
Yeah. I mean, we don't want to, we don't want redos. We want to do it and be done.
Right. And Project 3B results, I don't know, Board, do we have a ETA on that one and prizes? That's the next thing to work on.
We are done.
People were finishing it up until last week. Yeah, we should be able to post pretty soon.
This week, I think there was still a few people who left, had some circumstances that extended it. I think, maybe even tomorrow or something like that. So there are things that happened. We are trying to release those scores this week.
Good stuff. Again, thanks for all your patience. And we do hope this last 3 weeks isn't as crazy. I know you're working Project 4 and one project always is dominant, but hopefully you're learning a lot from it. This is a fun project for a lot of people. We will ask at the end what's your preferred, which is your favorite projects, and kind of rank them. And so a lot of people every year, years past say Project 4 is their favorite. People who like to do this parallelism stuff. So please do jump in on that. And we do find, by the way, the labs will help. Remember, labs are no longer required. They're out there. I mean, they're required in the sense that the material is still testable, but we're not going to ask you to just show us up for, show up for the check off. They're called check-ins now. But we do find that these labs are really good to do before you do the projects. You will learn about it and do it in lab to do the project. So please do the labs. But again, there's no rush on time. Just get them done before the projects, and you'll certainly find doing the projects much more fun and much easier to do. All right, folks. Thank you so much, Bor. Good to see you as always, my friend. We'll see you next week.
Thank you, Dan.
And thanks everybody. We'll see you, folks. Take care, everybody. Do well. Enjoy and enjoy. We'll see you before. We'll have one more visit before Thanksgiving. So we'll see you guys there. All right. Thanks, folks.
Thank you.
Bye.
Bye.